Okay, welcome back, everybody. Today I'm really excited because we get to finally move into chapter 14, which is all about functions of several variables. And this is basically taking everything you learned in Calc 1 and just extending it to functions of higher dimensions, or just into higher dimensions. It's super cool. Let me go ahead and pull up the slides and we'll get started. There is a bit of a Mathematica component to this, so we'll take a look at some Mathematica images. The activity is Mathematica based as well, so we'll do that in the computer lab for that activity. But here we go. So 14.1, stepping into functions of several variables. We'll talk about just functions of two variables to get our feet wet. We'll talk about graphs and graphs of these two variable functions. Then we're going to talk about level and contour curves, which are really important and really, really helpful. Then we'll talk about functions of three variables. And then we'll finish off with a little discussion about functions of several variables. So it's a packed lesson, but I don't think it'll be too long. Should be about standard average length. All right, so if you remember from the past, a real valued function is just a rule that assigns to each element in its domain a unique element, f of x, in the range of the function. So real valued functions are basically the same things that you know and love. You've been talking about them forever. You've got a domain, you have an element in your domain, you apply a rule to it, and then you get an element in the range of your function. That's what we're talking about. The real valued part just means that we're talking about functions that send things into the real numbers. So notice here that the range is actually the set of all outputs that are in the real numbers, and the only stipulation is that the input has to be within the domain of our function. Oh, maybe I kind of switch between indicating domains with and without a subscript, but that's the whole idea. So that's all still the same. Now, what is a real valued function of two variables? The basic idea is still the same. The only difference is now our domain can be a region in the xy plane. So let me go through the definition here. So it's still a rule, and it assigns to each element in the domain a unique element in the range, which is in the real numbers. Here's the catch. Now we're going to be taking these ordered pairs, these points that are in our domain, and we're going to map that point to some real number output. And the range is the set of all of these outputs, right? We often write z equals f of x, y, so that z is a function of x and y. And the variables x and y are both called independent variables, and z is what we call the dependent variable. So this is where things get really, really fun, because what you have to kind of open your mind to is that now we can basically take a point in the plane and we can map it to a real number. All right, that's the idea. So you give me a point in the plane, and I'm going to associate it with a real number, and that real number is the output of the function, right? So here's kind of a picture of it. You can visualize our domain as a region in the xy plane, and the output f of x comma y is a real number on the z-axis, right? So this is a pretty good picture of it right here. This is the xy plane. Pick a point in that little region, the region D, which is this kind of swoopy looking thing. Pick a point in there. We'll do this one. And then we're going to map that point to a real number called f of x comma y. So the f of x comma y is the output, and it's a real number. So this is one of the reasons why a lot of times these are called height functions, or maybe more appropriately altitude functions, when it's geometrically relevant. So the idea is kind of like, hey, if you've got a point down here on the plane, like, can you tell me how high up I should go from that point? And maybe how high I go up varies depending on where I am on the plane, right? That's the basic idea. That's the basic geometric intuition for it. Um, but it doesn't always have to be an altitude function. So remember, with all of this stuff, it doesn't really need a physical interpretation, but physical interpretations are very satisfying because we can see them and we're like, oh yeah, that makes total sense. Right, okay. Here are some basic examples. So temperature. At any point on the globe, if you want to know the temperature at some point on the globe, it's a unique number and it depends on longitude and latitude. So we could write that the temperature is some function of x and y, where x is the longitude and y is the latitude, or vice versa, right? So we can describe that, and you can get basically a temperature map of the whole world. Wind chill, for example, wind chill, it's dependent on the temperature and the wind speed. So you need two variables to describe wind chill. So we could describe it as a function of two variables, some function f that's dependent on temperature T and v for wind speed, that kind of stuff. Or how about this? So this is even like business majors. The profit that a business generates is dependent on revenue and cost. So even the basic idea of profit is a two variable consideration. Usually it's more, right? If anybody has any experience with running a business or has thought about it, clearly your profit depends on many, many things. So you can have functions of many, many variables here. That's the idea. In this case, we could say, hey, our profit is a function of revenue and cost. And then we can start to describe how, hey, if we alter the revenue, how does that affect our profit? If we alter the cost, how does that affect our profit? And then you can do all sorts of cool stuff with that. Um, Incidentally, for students that take business calculus, you do some multivariable calculus in a business calculus class if you take it at like a UC, for example. So even though it's, Calc 1, quote unquote, you will actually talk about functions of two variables in those classes. Okay, so where am I? There it is. Oh yeah, so here's a good example. We can talk about a two variable function in this regard. We'll say admission to Space Mountain at Disneyland requires that riders be between the ages of 5 and 100 years old, and they have to be between 44 inches and 120 inches tall, inclusive. So 44 and 120 are included, which is quite large, by the way. So that's, less than 4 feet, and this is a 10 feet. So if you're more than 10 feet, you can't ride the ride. That's what it means. So um, let's let A represent the age of the rider, H represent the height of the rider, and we'll let S be the function that outputs 1 if someone is allowed to ride, and 0 if someone is not allowed to ride. So this is kind of it's like a binary function. It's like a yes or a no, right? Yes or no. Do you satisfy these conditions? Yes. 1. Do you satisfy both of these conditions? If you don't satisfy both, that's a no, right? So this is one I want you to kind of try on your own, actually. At least just ponder it for a minute, all right? But see if you can write this function s as a piecewise defined function, a piecewise defined function. What is the rule for 1 and what is the rule for 0? All right, so ponder that for a minute. Okay, now say something out loud about how you might write down the function, like what structure should it have? Okay, and now try to write it down and we'll look at it together in just a moment. All right, here we go. So this is an example of what it can look like. So here is our function s of a comma h, and it's a piecewise defined function. So it's 1 if some conditions are met, and it's 0 if those conditions are not met. So here's one way you could describe it. You could say that the function s of a comma h spits out the number 1 if the point a comma h is an element of this region in the plane. So this is basically like a rectangle in the XY plane, a rectangle that goes from, maybe I could even, I'll do like a real quick sketch right up here. Here we go. Here's the rectangle. It goes from 5 to, oh wait, sorry, I have to label my axes. Here's A, here's H. So it goes from 5 to 100 in terms of age, and then it goes from 44 to 120 in terms of height. And so what you get is you get this region, this rectangular region in the plane, and this is the region on which, oops, this is the region on which our function is defined. I shouldn't say that, I apologize. Not the region on which our function is defined. Our function is actually defined on the entire plane R2, but on this pink region, this is exactly where the function will spit out the number 1. So this means, yes, you are allowed to ride Space Mountain. You're allowed to get on the ride, come on in, it'll be fun. Everywhere else is a 0. So everywhere else outside of that is just a big 0. That's what our function would spit out on those points, or on those regions, I should say. Um, because we're talking about like a physical thing here, it doesn't really make sense to talk about negative age or negative height. So realistically, there shouldn't be anything over in these regions, right? Like these regions don't make any sense in the context of our problem. So this is basically what our function looks like. The domain is all positive A's and all positive H's. Where does the function spit out the number 1? Right here on that pink rectangle. Where does it spit out the number 0? Everywhere else. So that's an example of a two-variable function. Here's a little note I have at the bottom. This is something that I know all the math majors will see this eventually, so we might as well mention it now. This set here, let me highlight it. This set 5 comma 100 cross 44 comma 120, that's what we call the support of the function. So the support of the function is the closure of the set where the function is not 0. So it's kind of you can think of it intuitively. The support is where your function is not 0. But some things interesting can happen at the boundaries, so we like to include the stipulation that the support is the closure of the set where the function is not 0, just because interesting stuff can happen on the boundary. But that's what the support is. Okay, all right, so now let's look at some more examples. Here's a two-variable function, f of x comma y. We're going to evaluate the function at the point 3 comma 2, and then we're going to find and sketch the domain of the function. So this is one I do want you to try on your own before I go into it, so think about it for a minute. All right, now say something out loud about maybe how you would evaluate the function. How would you evaluate it? Right, now try to do it on your own. Try to evaluate the function and then see if you can sketch the domain. A quick hint for that, remember the domain is going to be a region. It's going to be a region in in R2, in the xy plane. All right, now let's do it together. Simply enough, I mean, evaluating is pretty straightforward, right? You plug 3 in for x, you plug 2 in for y, and then you simplify and you will get a number. So that's what we get here. So what is f of 3 comma 2? It is root 6 over 2. So that is the real number output this function spits out when you put in the point 3 comma 2. Now for the domain, well, how do you find the domain? How you find it is basically the same way you did in the past. You just have to think about where these maybe I'll say, geez, I don't want to say it, like, I don't want to say component functions, but you need to look at all the pieces of your function and see where those pieces make sense, meaning that they won't error out. So one thing that I see as a problem right away is when x is equal to 1. If x is equal to 1, we're trying to have the function divide by 0. It's not going to be able to do it. It's going to error out. So we need to exclude the line x equals 1, and that's what you can see right here. There we go. So the line x equals 1 is excluded from this domain. Then we got to be careful about what's going on inside this radical. So since we're still talking about functions, we're talking about real valued functions, we don't have complex numbers involved. We could, and many of you will see complex valued functions. They're fundamental to mathematics and analysis and all sorts of different STEM applications. But for now, we're only dealing with real numbers. So the only way that this expression is valid is if this stuff in here is not negative. So you basically set x plus y plus 1 to be greater than or equal to 0, and that gives you your region of acceptability, I'll say. Which I say right down here in set builder notation. Again, this is another reason why set builder notation is so nice, because you can basically just say, hey, it's the set of all these points that satisfy these conditions, which is great. Now, this is the actual representation, the set representation of the domain. Here is a picture of the domain. So this is going to give you, or I should say, this, the equality, oops, auto, got it? Sorry, little pop-up I wasn't expecting. There we go. Yeah, there we go. Here, this is just going to give you a line, right? It's the line x plus y plus 1 equals 0. That's actually what this line is right here, indicated in the picture. So we just need everything on or above that line. That's what this condition says right here. And that's why we have this blue region up here. Then in addition to that caveat, we have this additional caveat, which is x cannot be 1. All right. So I'm going to pull up Mathematica here, and we're going to take a look at a graph of this particular function. But I just want to reemphasize that this is the domain of the function. This is the set of all the inputs of the function. And what our graph actually looks like is a surface in space. And that's what we're going to look at right now. So let me pull up Mathematica. Again, you can find this Mathematica notebook on Canvas, and you can mess around with it and follow along if you'd like. But here's the first one. So here's that function. Square root, wait, can you see? Yeah, you can see it. Maybe I'll zoom in a little more so it's a bit bigger. 200? Yeah, why not? Remember, these are just my options to make the graphs look pretty. Here's the first one, and we're going to investigate it just for a minute here. So this is square root of x plus y plus 1 divided by x minus 1. And I've restricted x and y just to be between -5 and 5 because we got to choose a restriction. So here's the picture right here. I'm just going to turn things a bit. There it is. Okay. There it is. I'll talk about all these details in just a second here. But first thing I want to do is turn this right side up. And notice that, come here. There it is. Okay, notice that this is basically exactly the picture we were just looking at when we were looking at the domain. Let me flash back real quick. There it is, right? Here we go. So some things to note about it. Here is that line, x plus y plus 1 equals 0. And then right here, this little slice that you're seeing, this is where x equals 1, right? Here's the x-axis, right? It's negative over here. It's positive right here. So this right here is when x equals 1. And that line is removed from our domain. So now if I tip this up a little bit, let me tip it back up here. You can see that what's happening is we actually have an asymptote. We have a planar asymptote at the line x equals 1. So even the notion of like an asymptote can be extended to planes and even hyperplanes and regions and all sorts of cool stuff. Another thing I want to say here is, remember, computers are not human beings, and so they cannot understand infinity, and they cannot contemplate the never-ending existence of reality or any of that stuff. So they're finite, and they got to chop things off at some point, and they got to approximate virtually everything. They're just approximating stuff. So what you're seeing here are artifacts in the image produced by the approximation algorithm that Mathematica is using to produce this image. You can even see some of the lines, like these little rays right here. Yeah, again, like computers cannot imagine perfectly smooth surfaces. They have to approximate surfaces using a triangulation or something like that. Even like if you think about video games, right? Like if you go back to something like the N64, everything looked really polygonal, like a bunch of triangles, because that was the best we could do back then. Now, if you do a whole bunch of those polygons, you do a whole bunch of those triangles, and you make them really, really tiny, you can get really, really close to an exact picture. So what you're noticing here are artifacts in the approximation process that the computer is using, right? It's not that the function like ends here. The function actually keeps going up forever and ever and ever, and it's asymptotic. So now instead of using like, yeah, literally like, am I doing it the right way? Wait, backward for you all. Like that. There you go. That's what's going on right here. But yeah, it keeps going. So that's the first one. So again, our domain is a two-dimensional region in the plane, and the graph of our function is literally a surface in space. Cool stuff. It just gets cooler. All right, so let's go to the next example. How about this one? Here's another one where I want you to try it again. Like try to do this on your own, and we'll take a look at it in a moment. So evaluate this function at the point 3, 2. That part's the easy part. And then find and sketch the domain. Try to sketch the domain this time if you didn't do it last time. All right, think about it for a moment. And then try to jump right into it. See if you can draw a picture of the domain and evaluate the function. All right, here we go. Um, Again, the evaluation is not so bad. We just plug this point in to our function, plug in 3 for x, and then 2 for y, and see what we get. So in this case, when we plug in 3 comma 2, we get 0. So the function is equal to 0 at that point. Now the domain is, well, let's see, what possible problems could come up from this function? Well, one thing, remember that the natural log function is only defined for positive numbers. So whatever we put into this thing, whatever is going into the natural log function, it better be positive, strictly positive. So what we need is, we need y squared minus x to be strictly positive. Or in other words, wait, that's not y squared. There we go. Y squared to be, in other words, we need y squared to be greater than x, right? That's the idea. And then if you look at where these are equal, you have a parabola x equals y squared. So that's this parabola indicated right here. And we need everything outside of that parabola. That's the idea. We need everything outside of that parabola, and not including the parabola. So this is the important part. This is actually a strict inequality. Strict inequality. So it cannot be equal to 0 because natural log of 0 is undefined. So that's why the dotted lines are used here. And then this blue region is the region of acceptability. These are all the numbers that the function can handle, that it can chew up and process. Yep, there we go. All right. Okay, so now let's take a look at the picture. Let's see what it looks like graphically. Let me go back to Mathematica here. All right, I've got this one plotted right here. One thing I believe I mentioned before, which is that generally, yeah, I did mention this before, capital LOG or just log means natural log in general. Yeah, basically natural log is the best log. So we like to reserve the word log for the best one. Log base 10, that's the log that you were calling log back in like high school and pre-calculus and stuff. But check it out. So I have x times log of y squared minus x. I'm restricting x and y to be between -5 and 5. And let me do this. Let me twist things a bit. Here we go. So it matches what we saw. All right, so this is like a bird's eye view, top-down view looking at our function, and this is exactly what the diagram of the domain looked like on the slides. Let me flash back for a minute. There it is. Right? There we go. So again, it agrees with what we would expect. Now, let me tip things up a little bit. Now you can again see that artifacting going on there, because again, there's an asymptote. So that parabola is actually an asymptote of the function. So here we have a curvilinear asymptote, or as I like to say, non-vertical asymptote, and it's in the shape of a parabola. There it is. Remember, the function does keep going on forever. So it goes down, the outputs, I should say, in the z direction. It's going to keep going down forever. The computer can't handle forever. It can't handle infinity or never ending anything. So we got to tell it to stop at some point. And there you go. And once again, our function is a surface in space. So you give me a point on the plane, and I'll tell you how far to go up or down from the xy plane based on this function rule. All right. Moving along here. So now you have a much better idea of what these graphs look like. So let's actually look at the definition. So if we've got a function of 2 variables with some domain in R2, then the graph of the function is the set of all points in 3 space, such that z is equal to the output of that function, and x comma y is in the domain. So again, this is an ordered triple. So x, y, z represents a point in 3-dimensional space. If we want to look at the graph of this 2-variable function, it's the set of all points where the z-coordinate is the output. All right, so the z-coordinate is the output, and the input is x comma y. Looks roughly like this. I had mentioned like a height function before, or an altitude function. That's what's going on right here. This is quite literally the output f of x comma y. So if your function happens to be positive, you could think of it as literally the height. So if I'm at this point, If I'm at this point on the planet, how high up do I go to be on the, or like at this point on sea level, how high up do I go? That kind of thing. All right. All right, this one, sketch the graph of this function. Let me see. I think this one let's just do together because we've done examples of this one a lot. So this one I won't pause. Let's just talk about this one. So here we've got a function f of x comma y, and it's given by this rule here, 6 minus 3x minus 2y. Well, everything here is linear. So what we're going to end up with is a plane. So this is exactly a plane in space. It's a plane with this equation, z equals x minus 3x minus 2y. And you can graph it by finding the intercepts just like we did back in chapter 12. So 2 is the x-intercept, 3 is the y-intercept, 6 is the z-intercept. And with those 3 points, you can graph the plane. Remember, the plane goes on forever. It's not stopping here. It goes on forever, but we can't depict that. We can't depict forever in a finite space. All right, let me show you what it looks like in Mathematica too. So here's what it looks like in Mathematica. Now I'm using, oh yeah, I should point out, now I'm using plot 3D, because we're in three-dimensional space. But here is what the function looks like, f of x comma y, and here's our plane. Simple enough, right? All right, now, yes, okay, so some other technical details. This leads us to this definition. So I mentioned this in an earlier lecture, but now I'm going to solidify it with this definition. A linear function of two variables. So a function that is of this form, like the form we just saw a moment ago, that's what we call a linear function in two variables. And this notion of linear function actually extends to any number of dimensions. And it's a very natural extension, right? If you remember the equation of a line, it basically was, this, like mx plus b. If you want the equation of a plane, now you need two variables, and if you want the formula for a hyperplane, you can just keep adding more and more of these linear terms in each variable. So x, y, z, t, p, q, r, s, however many you need. The graph of the function is z equals ax plus by plus c, or you can write it in standard form here like this. And we've seen this before, but yeah, basically a linear function of two variables is the natural two-dimensional generalization of a linear function in one variable. All right, how about this one? So this one I do want you to try on your own. And we've seen some stuff like this. So my hint to you is try to go with your gut, use your intuition to think what this could look like, all right? So think about it for a minute. Okay, now say something out loud about what you think it could be. Now try to write it. So see if you can draw a sketch. And I do recommend trying to do this one by hand, and then we'll look at it in Mathematica, just to give you some practice drawing it by hand. Oh, another hint, maybe square both sides and see what you get. All right, here we go. So using my little hint. Well, actually, do I really want to use my hint? Well, let me think here. So if I square both sides, I'm going to get g of x comma y squared equals 9 minus x squared minus y squared, which I can simplify a little bit. G of x comma y squared minus 9 equals negative x squared minus y squared. Multiply both sides by -1, 9 minus g of x comma y squared equals x squared plus y squared. There's some circular stuff going on here. And this is actually one of the reasons why I try to emphasize these types of structures in my pre-calc and calculus classes, because this is basically the formula of a sphere. It's kind of a generalization of the formula of a circle. Let me erase some of this junk. Oops. Right? Like if I were to scratch this out and I asked you to graph this, hopefully this looks a little bit familiar because that's literally just the top of a circle, right? That's the top of a circle of radius 3. Well, now that idea extends. Now what we have is we have the top of a sphere with radius 3. And that's exactly what it turns out to be, the top of a sphere of radius 3, just like so. There's the intercepts, 3, 3, 3, and it's a sphere. It's the top half of the sphere because we have the square root. We would actually have the entire sphere if we used the squared version that I had before I switched the slides over. So remember that when you take a square root, you get a positive and a negative, right? So this is actually taking the positive, oops, and that gives you the top of the sphere. If you wanted the bottom of the sphere, you would do the negative. Right. Oh yeah, let's take a look at it in Mathematica too, just so I can move things around a bit. Here we go. Square root 9 minus x squared minus y squared, and here it is. Remember, it's just the surface of this half sphere, of this hat. Yeah, it's the surface of the half ball. So it's not including the inside, just the surface. Ah, there you go. Another thing that we will see and address again in chapter 16, I believe. Take a look at the edges here. Do you see these little artifacts? And even if I try to kind of look down from the top, no, it's harder to see from the top. I take that back. Harder to see. Easier to see from this side. Well, what's happening is you're getting this artifacting on the edge because, well, look, our function is in terms of x and y. So our function is in terms of rectangular coordinates, wink, wink. But the object we are trying to describe is circular or spherical in nature. So we're trying to describe this circular object using rectangular coordinates, which really a computer can't do. It can or it can try, but it's not going to be so nice of a picture because it's kind of like squaring the circle. Really what we're trying to do is we're trying to approximate a circular boundary with a bunch of rectangles. And so it looks jagged, right? So maybe rectangular coordinates aren't the best way to describe such an object. Maybe there's another coordinate system that would perhaps better describe a circular or spherical object. I'll let you think about that. Think about that and we'll revisit it later in the course. Okay, all right, where are we? This one, okay, I want to move along a little bit here. There's just a bunch of examples at this point. So this one, you don't have to think about it or do it on your own. We'll do this one together just to start. Find the domain, the range, and sketch the graph of this. So this is basically an object that we saw back in section 12.6. It's a quadric surface. So the behavior you want to notice is that there's roughly circular behavior going on. However, because this number here is affecting the x term, it's going to stretch the circle. So this is really an elliptical behavior. So the what am I trying to say? If we were to look at this thing from top down, we would see an ellipse. We would see an ellipse that's been squashed in the x direction, right? Now, the output of this function is just a height. It's a height. So the input of our function is actually just an ellipse. It's an elliptical region, and the output is a height. But that height depends directly on the point in that elliptical region. And so from that, we get that. There we go. We get a paraboloid. There are no restrictions on x and y. You can put in any value for x and y that you want. I'll show you on Mathematica too. And then the height is going to be determined by what values you put in. Yep. What's the range? So the minimum value of a paraboloid is the vertex. So here's the vertex down here. That occurs exactly when x and y are both 0, because if they are positive at all, or negative at all, I should say, you're going to be moving up. You're going to have some change in height. So the range is actually 0 to infinity. Now let me look at it on Mathematica. Here it is. And it's just chopped off. I have it chopped off right here. But again, it would go infinitely up. It would go up infinitely. Keep going. All right. Okay, so next we need to talk about level curves or contour curves. Which term you use doesn't really matter. I find it really depends on how I'm feeling when I'm talking about them. But what is a level curve? So a level curve or a contour curve of some function of two variables. These are the curves in the xy plane where f of xy equals k for some constant k in the range of f. So maybe more intuitively, a level curve or a contour curve is the projection of the trace f of x comma y equals k. Sorry, tiny typo. There we go. It's the projection of the trace onto the xy plane. And then if you have a collection of these contour curves, a collection of these projections, we call that a contour map. A contour map. An example is like a topographical map, which I'll show on the next slide. The curves on the map are the contour curves. So do I say, oh, I say it in the next couple slides. So I'll hold off on that. Here's an example, two examples actually. So if you've ever gone hiking or if you've ever looked at topographical maps, this thing right here, this is a contour map. That's what it is. It's a contour map. And each one of these little curves that you see in the image, those are level curves or contour curves. And they're basically what you get if you were to slice the mountain at some altitude and then project the resulting curve down onto the plane. So right now we're basically looking down onto the mountain like that, right? And we're slicing the mountain at different heights and then projecting those curves of intersection down onto the XY plane. Here's a nice kind of isometric view. So here is the surface. This is the graph of our function, f of x comma y. You can slice it at different heights, and then you get these circular traces in space, these circular cross sections. All right. And then if you take all of those cross sections and you project them down onto the XY plane, you get what we call level curves. So these things down here, these are the level curves. These are the contour curves. And then the collection of them is a contour map. So I hope that makes a little more sense. Yeah, so some notes about these things. Contour maps are usually the most descriptive when the values of k are equally spaced, when you're doing slices at equal intervals. So we assume that they are unless stated otherwise. So we're assuming that the slices are evenly spaced, that when you're cutting it, at the same distance. This is, again, another thing I've been trying to get you all to practice visualizing and imagining three-dimensional objects and slicing them. I know I said that even like before the semester started, like if you want to get into Calc 3 right away, start doing this. Look at those three-dimensional objects. Imagine what a slice would look like if you could slice it and then take a peek at it. This is one of the reasons. This will help build your intuition for higher dimensional objects because this idea can and will get extended to higher dimensions. This is an important note too. It can be a little bit subtle, but level curves are different from traces or cross sections. So level curves are not the same thing as a level curve is not the same thing as a slice. What it is it's the projection of the slice onto the XY plane or the I'll just say the space where your domain lives. All right. So yeah, the level curves actually all lie in the XY plane, whereas the traces lie in whatever plane you made the slice. So there's a subtle difference there. But now maybe you can see why the Mathematica command contour plot is named as such. Sorry, another little typo right there. Because that's what it's doing. So the contour plot is basically creating a contour map by slicing at regular intervals this object and then projecting all of the images onto the plane. That's what it's doing. Yeah, okay, so here's one. We'll do this one together just to give you some more intuition before I send you out on your own, because it's going to get a little bit weirder in a minute. So sketch the level curves of this function for k equals -6, 0, 6, and 12. And actually, you know what? I take that back. Do try to do this one on your own. Try to do this one on your own, and we'll do the next one together. Yeah, that's what we'll do. So try to do this one on your own. Think about it for just a minute. All right, now give your brain some feedback. How would you begin? How could you proceed? Okay, and now try to work it out. So basically, plug in k for f of x comma y at these different values and see what the curves look like that you get. All right, let's do it together. So the level curves are what you get when you slice the thing, slice the region or slice the object at these different heights, I'll say. So if we set our function equal to k, and then we have all these different values of k, these are the results we get. So we get that, we get that, we get that, and we get that. And these are all equations of lines. So what happens is when you slice this object with different horizontal planes, you get lines. And this makes sense because if you remember, this function is a plane in space. So we're taking some plane and we're slicing it horizontally with other planes. And when you take a plane and you slice it with a plane, you get a line. So each one of the traces is a line in space. Then we project all of those traces down to the XY plane and we get the level curves. And then this whole collection is our contour map. That's what it is. Cool stuff, huh? All right, let's do a slightly more complicated example. We actually saw this one before. This one was that half sphere. And what I want to do is I actually want to show you what it looks like in Mathematica, and we're going to compare the actual object with its contour map. We'll do this again in the activity, and I have a couple more examples here. Where is it? Here it is. Okay. All right, so here once again is that sphere. The half sphere, sorry, this is the upper half of that sphere. And what I want you to do is just imagine you could slice it. Slice, 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 slice. And what you get, and then take all those curves. Every time you slice it, you're going to get a circular curve in space, right? Circle, and it gets a little bit smaller as you get to the top, right? So if I slice here, my circle is going to have a larger radius than if I slice up here. Now the circle has a smaller radius, and you keep going. And then eventually you get to a point where the thing doesn't exist anymore. So we keep slicing and then project all of those circles down onto the XY plane, and this is the contour map. This is the contour map right here. That's it. Cool stuff. And there's this big circle because remember the slices are at regular intervals. It's not like slicing at a bunch of random distances, right? They're all regular. So you can kind of see that as we're slicing lower, when k is closer to 0, well, the curvature, the height is changing faster. So that's why these concentric circles are closer together near the boundary, and they start to get farther apart the more you go toward the top of the sphere, because it's not rising as fast. So these start to stretch out a little bit. We're going to play around with this in the activity when we do the activity for this. But next, oh yeah, so I have a few more examples. These ones are actually from the book. But just to give you some ideas, let me zoom in a little bit. Take a look at this function right here. This is the function, here you go. This is the function negative xy e to the negative x squared negative y squared. This is what it looks like from isometric point of view and from a side view. Now imagine slicing it and imagine what curves you would get and then project them all down onto the xy plane in the middle there, and you get this. There you go. Okay, another example. This one. So here is the surface given by the function negative 3y over x squared plus y squared plus 1. And again, just imagine you could slice it and get a bunch of curves in space and then project all the curves down and you get this contour map. Cool stuff, huh? All right. Okay. Now we need to kick things up a notch a little bit. Now we got to talk about functions of 3 variables. This is where things start to get fun. So what is a function of 3 variables? Well, again, it's still just a rule, except now the difference is we're talking about ordered triples as inputs, so literally points in 3-dimensional space. And we're going to assign a real number, f of x, y, z, to this point in space. And that's pretty much it. So a function of three variables, I'm sorry, a real valued function of three variables is basically taking some point in space and tagging it with a real number. And you're going to do that for every point in your three-dimensional domain, your three-dimensional region in your domain. Yes, so now is when things get super interesting. And it's just so fun. Things get super duper interesting. And we can basically think of a function of three variables like this. Actually, I kind of said this a moment ago. Uh, f of x comma y comma z assigns a value to a point in space. It can be any real number. So you're just tagging a point in space with this real number. An easy example, again, doesn't have to be physical, or I shouldn't say physical. It doesn't have to be uh, what word am I thinking of? Geez, I can't remember. Geometric, maybe? Nah, doesn't matter. For example, the temperature at a point on the Earth, it depends on longitude and latitude, but it also depends on time. Like, there's a temperature right here where I'm standing in space, right? But the temperature changes depending on the time. So we can talk about temperature as a location given by latitude and longitude, and then also a time. And now we have a function of three variables. And so, yeah, this is where things get interesting. um, because you might be thinking, how would you even visualize something like this? In general, it is very difficult to visualize a function of three variables because it's representing a three-dimensional object whose graph lies in four-dimensional space. All right, four-dimensional space. We'll talk about this more. um, so we as human beings cannot visualize four-dimensional space very easily. I think there's maybe a few people on the planet who believe wholeheartedly that they are perfectly able to visualize four-dimensional space. I will admit that I have spent countless hours imagining what this would look like. Um, but there's good ways to get a glimpse at what these objects can look like by looking at the level surfaces or contour surfaces. So level surfaces are analogous to level curves for functions of two variables. Level surfaces are projections onto R3, that is the XYZ space, of the surfaces that have equations F equals K, where K is a constant. So you're still doing the same thing, except now you're going to have a bunch of surfaces instead of curves, all right? So this is where things get really mind-blowing. So this should just be like, you know, just exploding your mind trying to imagine this stuff. That's a good thing. That's a good thing. Let your mind explode. Let your mind wander. Let your mind go deep into your imagination about higher dimensional existence and reality and higher dimensional objects. Embrace it. Embrace it. It's super fun. Um, Yes, we're going to see some examples of this, and maybe it'll click a little more. But this is definitely something that you have to practice. So you really got to practice imagining these higher dimensional objects. All right. Um, Last little note I'll say here: if this point x comma y comma z moves along a level surface, the value of the function does not change. Okay, let's see an example. All right, here's a good simple example. Simple, quote unquote. Consider the function f of x comma y comma z given by x squared plus y squared plus z squared. So the domain of this function is all of R3. The domain of this function is all of three-dimensional space. You can put in any point in three-dimensional space into this function, and it will give you a real number output. If you did 0, 0, 1, this would be 1. If you did 1, 1, 1, this would be 3. If you did -1, -1, -1, this would be 3. So you can plug in any point you want in space, and you'll get a real number output from this function. So the domain is everywhere. The range is 0 to infinity. So remember, these are real valued functions. So the output is just a real number. The difficulty here is that it's hard to think of it as a height function anymore. The reason it was easy to think about height functions in the previous examples is because we live in a roughly three-dimensional space. So when you talk about putting in a point on the plane and getting out a height, it's very intuitive. You can probably get it right away. Now, you don't have that intuition as much. However, this picture is a good example. So what does the graph of this function actually look like? It consists of all three-dimensional balls centered at the origin. So this is a good time, again, to let your mind blow and just ponder this for a minute. The graph of this function is every three-dimensional ball centered at the origin. So this is where I'm going to ask you to ponder this. So now that your mind has been blown, reel it in just a tiny bit and contemplate. Okay, we'll go through lots of these. Um, yeah, so what does this function actually look like, the graph? I'm talking about every possible three-dimensional ball in space centered at the origin, every single one of them, right? Every single one of them. And the object is all of them at the same time. That's why it's difficult to visualize. However, what we can do is we can intersect this graph with a three-dimensional hyperplane by setting the output equal to some number. So when we set the output equal to some number, then what we get is we get a two-dimensional cross-section in the shape of a sphere, a two-dimensional cross-section. So again, this is very bizarre, but give your brain some time to process it. If we basically choose a k value, then we're not talking about every possible ball. We're basically snapping into a single sphere that has radius square root of k. So that's what this picture is. Okay, so if I let k be equal to, if I let k be equal to 1, we'll start with that. If k is equal to 1, then we end up with a sphere centered at the origin of radius 1. That's this little purple sphere in the middle here. Okay, that's a level surface of the object that we are actually investigating. All right, now if I set k to be equal to 4, then what I end up with is a sphere centered at the origin of radius 2. That's this little yellow one right here. Again, that single sphere is not the actual graph of our function. Our function is every single one of these possible spheres, every single one of them all at once, like that. So this is one way you could imagine like a four-dimensional object. Maybe if you've ever pondered your own existence as a higher dimensional being, this is a good way to get started. I like to think of this stuff because it makes me feel that like the manifestation that I have in this reality, my body, is basically just a level surface of who I really am. That's what you all are seeing. That is what you all are interacting with. We're all interacting with each other's level surfaces on this plane of existence. But who we quote really are is probably a higher dimensional being, and we're projected down here. All right. Okay. Let's get back to the math a little bit. um, here we go. If I set k equal to 9, then I end up with a sphere centered at the origin with radius 3, and that's this blue one on the outside. So this is a good one to ponder. So once again, maybe I'll, oh wait, no, I have more here. Here we go. Yeah, yeah. And yeah, if you project all of these traces, so each one of these is a trace in space, each one of these spheres. And if you project them all down onto XYZ space, you get this, and this is the contour map. So the collection of all of these traces is the contour map. That's what it is. Cool stuff. Cool stuff. Okay. Um, let's do a slightly different example. How about this one? We're going to use Mathematica to get a good look at it. Here we go. That's right, I made the code fairly simple. So we're going to do a contour map of this function right here. The function is x squared minus y minus z squared. It is a function of three variables, so the graph is actually it's a three-dimensional object in four-dimensional space. So all we can really do to visualize it is look at traces in space and then project them down onto three dimensions and then look at the contour map. So let's look at it. Here we go. This is what it looks like. Yes. Okay, yeah, this is what it looks like. Let me show you the code really quick. So I'd use contour plot 3D. Now again, maybe this makes a little more sense why it's called contour plot, because this is a contour map. This is a contour map of our three-dimensional object, and these are the two-dimensional traces. That's really what it is. Here, I just wrote each level curve like so. I could have used a loop and not had so many, but I just decided to list them all out. So here you go. Notice now I need to provide restrictions on x, y, and z because this is a 3-variable function, 3 inputs. So here we're saying, here's one, right, here, basically here's one trace. You set k equal to this, and then you project down onto 3-dimensional space, and this is what you get, all right? So it's like a saddle. It's basically well, each one of these level curves or level surfaces is a saddle, but the actual object being described by this function, oops, by the function f of x comma y comma z equals this, is every single one of these all at once, no matter what k value it is. So you could almost imagine like filling it all in, and that would be the actual object we're talking about. Wild stuff. Just wild stuff. Fun stuff, though. So I hope some of you are a little bit intrigued by this because this is one of the reasons I just fell in love with math. So if you've ever been pondering your existence and higher dimensional beings and all that kind of stuff, welcome to mathematics. It's fun. All right, let's go back to the slides. We just looked at this a moment ago. Okay, let's do this one. So here, let's just find the domain of a function. Here's a function f of x, y, z given by this formula. And do I have this in Mathematica? I do. And oh, that's right. I just picked one single level surface. Okay. So find the domain of the function. And this is one that I do want you to try on your own. Finding the domain is the same. Look for possible restrictions and then specify the restrictions. All right. So think about it for just a moment. Right? And now work it out on your own and just try to write down the domain. Just another hint, remember your domain is in 3 space. Okay, here we go. Let's do it together. So this one's not too bad. Remember, the exponential function is defined for everywhere, right? So there's not going to be any problems here. And it's also never going to be 0, right? So the exponential function is never 0 no matter what input you give it. So we don't have to worry about division by 0. The one thing we do have to worry about is the natural log function here because this relationship has to be greater than 0. So x minus y has to be greater than 0. So that means that y needs to be less than x, strictly less than x. So that's our domain. But again, remember, this is the set of all ordered triples in 3 space that satisfy this condition. All right, so it's a 3-dimensional domain. Yeah, what is this region here? This region is the half space. We call it a half space because it's like half of space, consisting of all the points to the left of the plane x equals y. Excuse me. Let's look at it in Mathematica. Here we go. So here's our function. I wrote the domain restriction like so, just to make things a little more easy. But this is what the function looks like. So that triangular prism you're seeing is the half space. That's the restriction. Ooh. This function's hard for Mathematica to graph quickly. There we go. Oh, another thing I'll point out is we're only looking at a single level surface here. That's it. So remember, it's hard to visualize these 3-dimensional objects in 4-dimensional space. But what we can do is we can look at a trace, or we can look at a level curve or a level surface, and that's what you're looking at right here. There you go. Wild stuff. Okay. All right, let's move along here. We're almost done. Yep. Yeah, almost done. So hopefully now your brain has been totally expanded and blown away. There's no need to stop at 2 or 3 or any number of variables. We can describe real valued function of many variables. So you do not need to stop there. The definition is the same. Real valued function of several variables. Well, now you have n tuples. Sorry, a little typo there, capital N. You have n tuples for however many dimensions you need to work with, and your domain is a set in Rn. And your function is real valued, so you're going to take some point in n-dimensional space and you're going to assign it a real number. So it's analogous to an altitude, but now not as easy to visualize. The range is the set of all real number outputs as long as, oop, that's a typo right there. That should say D. As long as that point is in your domain D. That's it. So if you want to know the shortcut, everything we just talked about right now, pretend you could do it for any number of dimensions. You don't, and it turns out you don't actually have to pretend. You can do it. Making sense of it, building intuition for it, proving things related to it, that's much harder. That's much harder. Um, but yeah, and again, n tuples can represent a lot of things. So our function f is just a rule that we want to apply to these n tuples. The inputs do not need to be physical points. So this is one way where you kind of have to break away, or a place where you have to break away from intuition. A lot of times these functions are not, the inputs are not physical points in space. They're just data points that we have, and our data happens to have a lot of parameters, right? Data can have all sorts of parameters. And we just want to apply rules to this data set. So yeah. So I've said this a bunch of times. Just keep an eye on toward generalization and how you can generalize these ideas, and if you can actually do it. Not everything can be generalized. Not everything can be generalized in a consistent way. So it's good to ask these questions. Um, yeah, but I'll say this. In most meaningful applications these days, the data set is multidimensional. It's not one variable, two variables, three. Usually it's any number of variables. And so a lot of the math research that you'll read nowadays is all about things that are n-dimensional or even non-integer dimensional. Here's here's an easy example that's not physical points. So let's say a company uses n different ingredients to make a food product, and the ith ingredient costs c sub I dollars, and x sub I represents the amount of the ith ingredient used. So you've got 50 ingredients that you need to use to make this food product. Each one of those ingredients has a cost associated with it, and we need a certain amount of each ingredient. So what is the total cost of the ingredients needed to make the food product? Well, we can write it as a multivariable function. So the cost is going to be a real number. We need a dollar amount, right? And it's going to be given by this function right here, this rule. The cost of the first ingredient times the amount needed, plus the cost of the second ingredient times the amount needed, plus the cost of the third times the amount, plus the cost of the fourth times the amount, dot, 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 all the way up until the nth ingredient. And so our total cost function is literally this right here. Maybe this looks familiar to some of you. C1x1 plus C2x2 plus C3x3. Think about it for about 5 seconds. um, because notation can get very messy very fast when you have high dimensions, a lot of times we will just write bold x and talk about the position vector that corresponds to that point. And then we can just write our multivariable function as f of x, or our function of multiple variables as just f of x, where it's understood that x is an n tuple, or it's the position vector of an n tuple. That's the idea. Then we can rewrite the previous example, the previous function, like so. Our cost function, our total cost function, is literally just the dot product between the cost vector and the amount vector. And that's it. So it's a conciseness that we're looking for, right? That's what this gives us. So in this case right here, x and c are both n-dimensional vectors, and we're going to use the one-to-one correspondence between Rn and Vn that we get through position vectors. So that's another way to do it, right? So now we have 3 different ways of viewing a function f defined on n-dimensional space. You can think of it as a function of n real variables individually. You can think of it as a function of a single point. You put a single point into the function and it gives you a result. Or you can think of it as a function of a single vector variable, where this is the position vector of that n-dimensional point right here. And that's how we can imagine these types of things. So just to round things off one last time, hopefully this is about how you're feeling right now. That's okay, don't worry, that's normal. I encourage you to, frankly, just dream and imagine about these things because it gets really, really fun. It's just such cool stuff. All right. So on that note, let's play. I'm excited to talk to you all about this. I'm excited to do the activity for this. And for most of you, this is like just the beginning. This is just the beginning of stuff. All right, I'll stop rambling. Thank you again for watching, and I will see y'all next time.